we will discuss about DC response of an RLC circuit. So RLC circuit, here we are going to discuss is the series RLC circuit, and consider a circuit consisting of resistance, inductance and capacitance, and which is shown in the figure. And we are applying a voltage, DC voltage V, and there is a switch and which will limit the current flow through this series circuit, and here it is shown that the switch is open and there is an arrow mark, that means the switch will be closed at a time t equal to 0. Since the time is not mentioned here, that means we have to assume that the switch will close or switch will coming to this position when time t equal to 0. So once the switch is open, there is no current through this circuit. So when the switch is closed, that means the circuit will be a closed circuit in which resistance, capacitance and inductance are in series with this voltage source. So we can apply the KVL in this loop. So by KVL we can write V is equal to voltage drop across R, which is R into I, voltage drop across L, which is L into di by dt, plus voltage drop across C is 1 by C into integral I dt. So this is the Kirchhoff's voltage law equation for this series RLC circuit. So in this equation there are integration term and differentiation term. In order to avoid this, we have to, for avoiding the integration term, we have to differentiate the complete equation. When we are differentiating this, you know that V is a constant value, so differential of V will be equal to 0. Then R into differential of I is di by dt, plus L into, once again we are differentiating this, that is d square I by dt square, plus integration of this quantity. So differentiation of this quantity, we are taking the differential. I think I have said that I am taking the integration. The differential operation is going here, and so the differential of this third term will give 1 by C into I. So the integral term will be disappear because we are taking the differentiation of the entire term. So we will get an equation 0 equal to R into di by dt plus L into d square I by dt square plus 1 by C into I. Here you can change this equation as R into capital D. See, that will this equation can be changed or written in this form, like d square plus C. Instead of d by dt, we are using the term capital D. Here d square term comes, so we are using d square plus R by L into, here also another d by dt term, so d comes, plus 1 by L equal to 0. This is the characteristic equation. This is a second order equation and this is a linear differential equation, and we are taking the characteristic equation like this, that is d square plus R by L into d plus 1 by LC equal to 0. Here I is the unknown quantity. So we can find the solution of this equation, solution of this characteristic equation. You know that once you have an equation like ax square plus bx plus c equal to 0, you can easily find the solution by x equal to minus b plus or minus root b square minus 4ac by 2a. Similarly, you can apply that relationship here. So you will get the unknown quantity. So d1 comma d2 equal to, here instead of b, R by L comes, minus b is minus R by L plus or minus root b square is R by L all square minus 4ac is 4 by LC whole divided by 2. Here a is equal to 1 and b equal to R by d and c is equal to 1 by LC. So by reducing this equation, we will get minus R by 2L plus or minus root R by 2L all square minus 1 by LC. So in this term, for EC notation, we are taking K1 equal to minus R by 2L and K2 equal to this term. Okay, so we can simply write the equation D1 equal to K1 plus K2 and D2 equal to K1 minus K2. Here K1 is this quantity and K2 is this quantity. So based on the value of K2, that may be positive or negative or 0. When K2 is positive, that means K2 is this one. When K2 is positive, means this term is very, very greater than this term, 1 by LC. So we can write R by 2L all square is greater than 1 by LC. In such cases, square root is a positive quantity. So the roots will be real and unequal. See, the roots will be real and unequal in the case of this equation. So the solution of that equation will be is in the form of d minus k1 plus k2 into d minus k1 minus k2 into I equal to 0. Solution will be I is the unknown quantity. So I will be c1 e raised to k1 plus k2 into t plus c2 e raised to minus k1 minus k2 into t. See, this is a differential equation. We have get the values of d1 and d2 as k1 plus k2 and k1 minus k2. So we can write the characteristic equation in this form. That is d minus k1 plus k2 into d minus k1 minus k2 into I equal to 0. This is the characteristic equation itself. And the solution will be is in the form of I will be equal to, we know that d is d by dt. So I will be equal to c1 into e raised to k1 plus k2t plus c2 into e raised to k1 minus k2 into t. So this is an important quantity. This is the solution of this type of equation. So when the roots are real and unequal, the roots will be like this, and when the roots are real and unequal, the nature of the response, if you are giving a DC voltage, then at the output the DC voltage will appear like this. That means the DC voltage will be over damped. See, here is a, you know that input is a DC voltage V. It is a constant value. When we are giving this input to this circuit, and when the roots of that equation is real and unequal, then at the output you will get a over damped response like this. So actually you have to get a single DC value here, but instead you are getting a damped, that means reduction in the amplitude. So that is it is called over damped response. Similarly, there is another case when R by R by 2L all square will be less than 1 by L. See, in such cases the terms, that means this term is negative, this term will be negative, so the roots will be imaginary. So the roots are, we can say that the roots are complex and conjugate, and so in such cases the differential equation you can, or characteristic equation can be written as d minus k1 plus j k2 into d minus k1 minus j k2 into I equal to 0. So this will be the differential characteristic equation, and this will have a solution. That is d minus k1 plus jk2 into d minus k1 minus jk2 into I equal to 0 is the characteristic equation. Its solution will be I equal to e raised to k1t into c1 cos k2t plus c2 sin k2t. So when the roots are unequal and imaginary, then the solution current will be, or unknown quantity will be in this form. And for such type, you can see that there is a presence of cos and sin terms, so it will represent the oscillation. The response will be oscillating in nature. You can see damped. So the current curve for this, suppose if we are taking the current as the response, then the current curve will be under damped. See, this is the reduction in amplitude, so there will be oscillations, and that oscillations will be under damped. And next case is, see, we have analyzed two cases. In some cases k2 will be 0. So in such cases, when k2 is 0, that means R by 2L all square is equal to 1 by LC. In such cases, the roots will be equal, because there will be no plus or minus term. So the roots will be equal, like minus b by 2a. So we can write the equation as a characteristic equation d minus k1 into d minus k1 into I equal to 0. So its solution will be in the form I is equal to e raised to k1 into t into c1 plus c2 into t. So this is the solution. That means when the roots are equal, then the solution of that circuit will be I equal to e raised to k1 into t into c1 plus c2 into t. So there are three cases, and this third case represents the critically damped case. So the current curve will look like this, and it has a similar value at the similar value of the applied voltage at the peak. So we have discussed three cases, and you have to remember the solution equation like I equal to this equation, and another equation is this one, and you have to remember this equation, and also you have to remember this equation. So next we can try to do a problem. So this question is, circuit shown in figure consists of resistance, inductance and capacitance in series with a 100 volt constant source. When the switch is closed at t equal to 0, find the current transient. So this is a series circuit, RLC circuit, and voltage is 100 volt, and there is a current I. So you have to find out the value of I in this case. And you can start doing this problem as given in the previous case. So you know that at the time t equal to 0, switch S is closed. When 100 volt source is applied, 100 volt source is applied to the circuit, and the resulting differential equation will be, see, when t equal to 0, switch will be closed, so this circuit will become a series circuit. So you can write the equation as 100 is equal to 20 into I plus L into di by dt plus 1 by C into integral I dt. So that is the equation, you know that. So you can write 100 is equal to 20I plus, here L, instead of L you can write 0.05, and instead of 1 by C you can write 1 by 20 into 10 raised to minus 6 into I dt, integral I dt. So you can solve this equation as in the previous method. This is a differential equation. First you can avoid this integration symbol, so you have to differentiate this equation again. So you will get differentiation of 100 gives 0, that is 0 here, and this is 20 into di by dt, that is shown here, and 0.05 into di by dt will go to 0.05 into d square I by dt square, and this term will be 1 by 20 into 10 raised to minus 6 into I. So when we are differentiating it, we will get this equation like this. So we can rearrange this equation by dividing all the terms by 0.05. So this term will become d square I by dt square. Second term will become, when we are dividing by 0.05, it will give 400 into di by dt. And this term, third term will give 10 raised to 6 into I equal to 0. This is simple mathematics. That is, we are dividing each term with 0.05. So this is a linear differential equation. So we can write this equation as d square plus 400d plus 10 raised to 6 into I equal to 0. So we have to find out the value of d1 and d2. So we can simply apply the minus b plus or minus root b square minus 4ac by 2a. So we will get the value of d1 and d2 as, instead of b we are writing 400, instead of c 10 raised to 6, and instead of a 1. So we will get minus 400 by 2 plus or minus root 400 by 2 whole square minus 10 raised to 6. So we will get the solution as minus 200 plus root 200 square minus 10 raised to 6 is one root, and minus 200 minus root 200 square minus 10 raised to 6 is another root. That is d1 and d2 we can solve like this. So this will give a minus 200 plus j 979.8 and d2 minus 200 minus j 979.8. You know that here the roots are complex conjugate. So the solution will be in the form of, as we have discussed in the second case, that is I will be equal to e raised to k1t into c1 cos k2t plus c2 sin k2t. So you should by heart this equation, and this solution is in the case of a complex conjugate roots. So we can substitute for k1 and k2. k1 is minus 200 and k2 is 979.8. So you can simply substitute for the values of k1 and k2. You will get an equation like this. So in this, c1 and c2 are unknown. So we have to find out its values. For getting the values of c1 and c2, that are initial values, we are using initial conditions. Initial condition means initially you see that the circuit is open, and at a time t equal to 0, the switch will be closed. So we are applying the initial condition as at a time t equal to 0, what will happen to this current? You can see that at a time t equal to 0, the switch is closed. We are assuming that there will be a current flow, right? But there is an inductance at first. You have studied about the characteristic of inductance, that inductor cannot change the sudden current. Inductor cannot show the sudden changes in the current. You know that. So at a t equal to 0, we can say that the current flowing through the circuit will be equal to 0. So I equal to 0, that means I will be equal to 0. So we can substitute, so in this equation I will be equal to 0, and instead of t we can substitute the value as 0. So we will get 0 will be equal to 1 into c1 cos 0 plus c2 sin 0, because t equal to 0, that means this equation will become like this. In this equation sin 0 equal to 0, so we will get cos 0 equal to 1, so we will get c1 equal to 0. That means in this expression for current, this term will disappear. So the net equation for the current I will be equal to e raised to minus 200t C2 into sin 979.80 A ampere. This is the equation for the current. In this equation also there is an unknown C2, but we will not get the value of C2 by just simply substituting the value of t equal to 0. So we have to go for another solution. So we will differentiate the above equation, that is di by dt will be equal to, you know that there are two functions, that is e raised to minus 200t and sin 979.80. So differentiation, there is a rule for differentiation, first function into derivative of second plus second function into derivative of first. So when we are differentiating it, we will get the equation as a c2 into e raised to minus 200t into, when we are taking the differentiation of sine term, it will give a cos 979.80t and there is a constant term 979.80t plus next second function is sin 979.80 plus in the differentiation of e raised to minus 200t is e raised to minus 200t into minus 200. So there is a differential equation, and in that equation we are putting the condition t equal to 0, that is at a time t equal to 0, you know that at a time t equal to 0 switch will be closing, and so there is a need to so it is essential that when the switch is closed, that means there is a closed circuit is formed, and we will assume that there will be a flow in current, but you know that inductor has a property, it will not shows the sudden changes in the current. So once the switch is closed, we expect that the current will flow through the circuit, but actually the current inductor will oppose the flow of the current, so that it will at a particular time, that is at t equal to 0 plus, the inductor up to that time t equal to 0 plus, the inductor will remains open circuit, that means it does not allow the flow of the current through it. So once it is open, that means the complete voltage that is applied here will appear across this inductor. When a part of the circuit is open, means that all the voltage will appear across that part. So when t equal to 0, the inductor will not allow the flow of the current immediately, that means it will remain open at that time, that means the complete input voltage will appear across this inductor. So we can say that the voltage across the inductor will become 100 volt. So we can substitute that volt. We know that voltage equation for inductor is L into di by dt. So L into di by dt equal to 100, we know that, and in that case L is given, that is 0.05 Henry. So di by dt will be equal to 2000. So at t equal to 0, di by dt is equal to 2000. So we can have an equation di by dt equal to this quantity. So we can substitute that value in this equation. So we will get 2000 equal to C2 into 979.8 into cos 0. See, sin 0 terms will disappear because sin 0 equal to 0. So we will get the value of C2 as a C2 equal to 2000 divided by 979.8, that is equal to 2.04. So the current equation will become, we have the current equation, see this is the current equation, I equal to e raised to minus 200t into C2 into sin 979.8t. So the current equation I will be equal to e raised to minus 200t into 2.04 sin 979.8t ampere. So this is the solution for the RLC circuit, and you have to know the complete equation, 3 cases equation, and we have to know to substitute the initial conditions, and for that you should know the working of each and every component. That's all about this topic. Thank you.